Hello everyone, welcome to the channel Top Gate. In this video, we'll study a new concept, that is the minimization of DFA. So in this lecture, we'll first try to understand that what is the need of minimization of DFA, and then we'll see how to minimize a particular DFA. So here you can see there is a DFA, this is a DFA, and I just have converted this DFA into the transition table. So this is your transition diagram and this is a transition table. So in the exam you might get this transition diagram or you might get this transition table. Both are just the same thing, just different representations of the same machine. Okay, so if you get this transition diagram, you need to convert it to the transition table because this will make your work a little bit easier. Okay, so first of all, we'll try to understand that what is the need of minimization of DFA. So we all know that whenever we have a problem, and for that problem if I have to make a NFA, clear? So if I have to make a NFA, now this NFA has to be converted to a DFA. Why? Because we know that DFA is a complete system in itself. So suppose for a problem I have made a NFA, this NFA contains n number of states. So now if I convert this NFA to a equivalent DFA, then the DFA will contain 2 to the power n number of states. So in the NFA we have less number of states, and in the equivalent DFA for the same NFA we have more number of states. So we can say that this DFA might be complex as compared to the NFA. Clear? So while converting this NFA to a DFA, it might contain several solutions, and all those solutions might be having more number of states, and therefore it will be having more complexity. So in order to reduce this complexity, I need to minimize this DFA. That means I need to remove all those states from this DFA which are actually not taking part in producing the final output of the machine. So a DFA and the minimized DFA, they both will be equivalent in the terms of that they both will be producing the same set of outputs. Clear? So this is a need of minimizing of this DFA. Now for minimization of this DFA, there are two different methods we follow. The first method is the partitioning method that we'll try to see in this video, and there is one more method that is called as the Myhill-Nerode theorem. So in this video we'll focus on the very first method, that is called as the partitioning method. Clear? So in this partitioning method, if we have to minimize this DFA, so it has actually two steps. The first step says that the step 1 of this particular method, it says that we have to remove all those states from this DFA which are not reachable, from the initial state. That means here I have Q0 as the initial state, Q2 as the final state. There is a possibility that there are several states which are not reachable from the initial state. That means if I start the journey from Q0, I am not able to reach on to that particular state. So that particular state needs to be removed from this DFA. Why? Because it is not taking part in producing any particular output for this DFA. So if we see from Q0, if we talk about Q1, so Q1, it has a direct reachability from Q0. So Q0 to Q1 I can reach on with 0 input. Similarly, if I talk about Q2, so Q2, if you see that from Q0 you can go on to Q1 and then you can go on to Q2. So Q2 also there is a reachability. Reachability can be either direct or it can be indirect, no problem. But there should be some route available from the initial state to that particular state. That will be a reachable state. Otherwise, if there is no path, then that state is a not reachable or unreachable state, and that state has to be removed from this particular DFA. So if we talk about Q3, so Q3, if you see that Q3 does not have any incoming edge and there is no path from Q1 which I can follow and reach on to Q3. So there is no path, I cannot reach on to Q3 at any cost. Therefore, this Q3 is a unreachable state. Clear? So in my procedure, I will not consider this Q3 at all. Why? Because this Q3 is a unreachable state. Now if I talk about Q4, so if you see Q4, there is a path from Q0 to Q5 and then Q5 to Q6 and then Q6 to Q4. So Q4 is fine. If I talk about Q5, Q0 to Q5 path is there. If I talk about Q6, Q0 to Q1 and Q1 to Q6 path is there, no problem. If I talk about Q7, then again Q0 to Q1, Q1 to Q6 and then Q6 to Q4, Q4 to Q7. So there is a path available to Q7 also. So all the states are reachable except this state Q3. Therefore, I will not consider this particular state in the minimization of the DFA. That is your step 1. Now the step 2 says that I have to divide these states into 2 sets. The first set will contain the final states and the second set will contain the non-final state. Okay, so that is called as the equivalence of the states. So first of all, I'll try to calculate the 0 equivalence called as the pi 0, and pi 0 I will keep 2 sets. Clear? That will be, first is the final and second is a non-final. So if I talk about the final state, just mark it here. Q0 is the initial state and Q2 is the final state. Clear? So if I talk about the final and non-final, then I have Q2, which is the final state, and then in next set I have Q0, Q1, Q3 I will not consider. Why? Because it is not reachable. Then Q4 and Q5, Q6 and Q7. Now this I will call it as set number 1 and this I'll call it as set number 2. Okay. Now set number 1, it has only one single element, so I don't have to do anything else with this one, so I'll keep it as it is. And set number 2, you can see that it has 1, 2, 3, 4, 5, 6 states. Now this set 2 has to be partitioned. Now how will I partition it? So now I'll make a table for this set 2. So I'll make a table for set 2, that is, I'll write state here and then I will write set of state for 0 and then I'll write set of state for input 1. Clear? Okay, so now in set 2 I have 1, 2, 3, 4, 5, 6 states. So I'll write all those states here: Q0, Q1, Q4, Q5, Q6 and Q7. So now for Q0, you take this Q0 from here and just come to the main table. For Q0, for input alphabet 0, I have Q1. Now this Q1, I'll see in pi 0 in which set it is appearing. So if we talk about Q1, this Q1 is appearing in set number 2. Clear? So I will write set number 2 here. Correct? Again, for Q0, input alphabet 1. So for Q0 1, I'm getting Q5. So Q5, and now I'll see in which set it is appearing. It is appearing in set number 2 again. So I'll write set number 2 here. Fine. Now Q1. Q1 again, I'll just check it here. Q1, I'm getting Q6. So Q6 belongs to set number 2. So I will write set number 2. And similarly, Q1 for 1, I'm getting Q2. Q2 belongs to set number 1. So I will write set number 1 here. Similarly for Q4. So for Q4, I'm getting Q7. So Q7, it is set number 2. I will write set number 2. And then it is Q5. Q5 belongs to set number 2. So I will again write set number 2 here. Now Q5. For Q5, I'm getting Q2 and Q6. Q2 is set number 1. Set number 1. And Q6. Q6 is set number 2. Correct? Now Q6. Q6, I'm getting Q6 and Q4. Q6 is set number 2 and Q4. Q4 belongs to set number 2. I'll again write set number 2 here. Similarly, Q7. Q7, I'm getting Q6 and Q2. Q6 is set number 2. Q2 is set number 1. So this I have made the table for this particular set number 2. Now if you analyze this one, if you observe that Q0, Q4 and Q6, that is Q0 has 2, 2, Q4 has 2, 2, Q6 has 2, 2. So you can see that Q0, Q4 and Q6, they both are, all these three are similar. And similarly, if you see that Q1 it is having 2, 1, and then Q7 it is having 2, 1. So Q1 and Q7, they both are same. And there is Q5 which is having a different set, that is 1, 2. So I'll write Q5 5 here. So now this set number 2 is further divided into three sets, and we call this as set number 3, set number 4, and set number 5. Clear? So I'll just rub it now. So now I got my pi 1. In pi 1, what I can have, this remains the same, that is q2, and then the set number 2 is divided. I have got q0, q4, q6, and I've got q1, q7, and I've got q5. So now let's call this as set number 3, set number 4, set number 5. Clear? So now I have this set number 1, set number 3, 4, 5. Set number 2 is broken into 3 number of sets, 3, 4, and 5. So I'll continue to do this unless and until this division is not possible, or I get a single element into the set. So now I'll make a table for set number 3. So let's make a table for set number 3. I'll just write set 3 here. Set 3, again I'll write state, and then set of state for 0, and then set of state for 1. Correct? Again I'll write it here, q0, q4, and q6. Okay, now q0 for 0, q0 for 0, I'm getting q1. Now this q1, I'll now check it in pi 1, because pi 0 is obsolete now. Pi 0's set number 2 is gone. We have got 3, 4, and 5. So now I'll look into pi 1. So for q0, I'm getting q1 and q5. So q1, if you see, it is set number 4, and q5, if you see, it is set number 5. Fine. For q4, if you see, we have q7 and q5. So q7 belongs to set number 4, and q5 belongs to set number 5. Similarly, q6. For q6, I'm getting q6 and q4. q6 is set number 3, and q4 is again set number 3. So if you observe, you can see that q0 and q4, they both are having the same sets, that is 4, 5 and 4, 5 and q6. Therefore, we can say that now set number 3 can be further broken into two sets, that is, I have now q4 and I have now q0 and q4, and I have q6. So now I'll just divide this set, and I've got a new pi now that is called as the equivalence 2. So now I've got my pi 2. In pi 2, what I'll get? q2, it will remain as it is, and then this is broken into q0, q4 and q6, and this will remain the same, q1, q7 and q5. So this remains the same, that is, it will remain set number 4, set number 5. Set number 3 is broken, so I'll name it as set number 6, set number 7. This remains the same, set number 1. So now I have set number 1, set number 6, set number 7, set number 4, set number 5. Now I'll again do the same procedure for set number 6 because it contains 2 elements. Then I'll follow the same procedure for set number 4. It contains 2 elements. Set number 7 is fine, it has only a single element. Set number 5 is fine, it has only a single element. Set number 2 is fine, it has only a single element. So now I'll make a table for set number 6. So now let's make a table for set number 6. Okay, so set 6, again same thing. I'll write state here, and then for 0 and for 1. Clear? Now elements that I have is q0 and q4. So q0 and q4. So for q0, I am getting q1 and q5. So if you see q1 and q5, so q1 belongs to set number 4, q5 belongs to set number 5. Similarly, q4, I am getting q7, q5. q7 is 4 and 5. So 4, 5. So you can see that both are again the same. So there is no need to divide this. So this set number 6 will remain as it is. Clear? So that is fine. Now we'll move on to set number 4. For set number 4. Now set number 4 contains Q1 and Q7. So I'll write Q1 and Q7. For Q1 I have Q6 and Q2. So Q6 is 7 and 1. So I'll write 7 and 1. And for Q7 I have Q6 and Q2. Q6 is 7 and 1. So again you can see it is the same number of sets. Therefore I cannot divide this set number 4. Clear? So that is all I think in this one. I cannot divide this number of states further. So this is my required DFA. That means in my DFA I have got 5 states. In this particular DFA I had 8 number of states, but in the minimized DFA I have got 5 states. 1, 2, 3, 4 and 5. State Q0 is combined with state Q4 and state Q1 is combined with state Q7. Now the DFA that I'll get in the end will be the same as the DFA that we have started the journey with. Why? Because they both will be producing the same set of outputs. So now let's see how we can get the final DFA. Now this pi 2, it contains 5 number of sets. Now these 5 number of sets will be your states for the minimized DFA. So let's make a table for the minimized DFA. I'll make a table here, that is state and then 0 and then 1. Clear? Now the states that we have is this Q2, Q0, Q4 and Q6, Q1, Q7, Q5. If you see the main diagram, in this one the Q0 was initial state. So here there is no Q0. Q0 is merged with Q4. So Q0 and Q4 will become my initial states. So I have got Q0, Q4, that is a single state and it is the initial state. Correct? Now we see from Q0, Q4 with input alphabet 0. So I'll just come here and I'll see from Q0 and Q4 with input alphabet 0, I'm getting Q1 and Q7. So I'll see that do I have Q1, Q7 here? Yes, I have Q1, Q7. So I'll just simply write Q1, Q7 here. Clear? Similarly, Q0, Q4, 1. So Q0, Q4, 1. I'm getting Q5 and Q5. So I'll just simply see that Q5 is available here. Yes, it's available here. It's Q5. So I'll write Q5 here. Next state I'll take, say, as Q1, Q7. I have this Q1, Q7, so I'll take Q1, Q7 here. So now Q1, Q7 again for 0. So Q1, Q7 for 0, I'm getting Q6, Q6. So I'll see if I have Q6 here. Yes, I have Q6. So I'll simply write Q6 here. Similarly for 1, so Q1, Q7, for 1 I'm getting Q2, Q2. So I have Q2 here. Yes, I have Q2. So I'll simply write Q2 here. Done? Next one I'll take is, say, Q6. Now for Q6, what are you getting? For Q6 I'm getting Q6. Q6 is here, so I'll simply write Q6 here. And I'm getting Q4. So Q4, if you see, there is no Q4. Q4 is merged with Q0. So instead of writing Q4 here, I'll write Q0, Q4. So I'll write Q0, Q4 here. Done. Next one I'll take, say, which one is left? Q6 is done, this one is done. I'll take Q5. So Q5. Q5, see, I'm getting Q2. So Q2, it is available. So I'll simply write Q2 here. And Q5, 1, I'm getting Q6. Q6 is available here. So I'll simply write Q6 here. Clear? Now the last one is left, that is your Q2. And for Q2, 0, I'm getting Q0. Q0 is not available. Q0 is merged with Q4. So I'll write Q0, Q4 here. And for 1, I'm having Q2. Again, Q2 is available. I'll simply write Q2 here. So this is the table for the minimized DFA. Clear? So if you have to make the transition diagram, you can simply make the transition diagram of this particular DFA. So let's make the transition diagram of this particular DFA. It's quite simple. We just have to convert this table into the equivalent transition diagram. So we have 1, 2, 3, 4, 5 number of states. So I'll simply take those 5 states. First one is Q0, Q4. That becomes my initial state. And then I have Q1, Q7. And then I have Q6, I have Q5, and I have Q2. Okay, so Q2 was the final state. So here also we have this Q2 as the final state. So I'll just simply make a double circle. This becomes my final state. Okay, now see, Q0, Q4 with 0, I'm moving on to Q1, Q7. So with 0, Q1, Q7, with 1, Q5. So with 1, I'm moving on to Q5. Q1, Q7, Q6, Q6 with 0, and Q2 with 1. Q6 to Q6, that means a self loop of 0. Q6 to Q0, Q4, that is with 1. Okay, then Q5 to Q2, Q5 to Q2 with 0, and Q5 to Q6 with 1. Clear? And Q2 to Q0, Q4, Q2 to Q0, Q4 with 0, and Q2 to Q2 with 1. So this becomes my final DFA. So this is a transition table for the minimized DFA, and this is the equivalent transition diagram for the minimized DFA. So you can see here in the DFA I have total of 8 number of states, and in the minimized DFA I have got only 5 number of states, and they both will be producing the same set of outputs. So we can say that both of these machines are equivalent. That is all. Thank you so much.